Okay, welcome to 8.2. For the same reasons as in Chapter 7, we're going to talk about proportions first, and of course that's because we can use z. So all of our intuition about the normal distribution comes into play. The first thing we need to declare is our random variable, that is the number of successes, and p, that is the proportion of successes. So the proportion, of course, comes from the population. That's a p, not a p hat, so that's a population proportion. And the x is from our sample. It's actually how many successes we had. The second thing that we need to do is check three things: that there's a simple random sample and a fixed size n, and that the conditions for a binomial distribution are satisfied. Now, when we saw this before, we said that n times p hat and n times q hat had to be greater than or equal to 5. And that's true. But with a little algebra, and having done this a few times, you'll notice that that's exactly the same thing as saying that x is greater than or equal to 5, and n minus x is greater than or equal to 5. And that's usually a whole lot easier to check than doing the multiplication. It's not a big deal, so if you continue using n times p hat and n times q hat, that's fine. Just notice there's a shortcut there. Now, our confidence interval for a population proportion is made out of the sample proportion p hat and the margin of error e, just like we said in 8.1. So we subtract e to get the lower bound, we add e to get the upper bound, and those are bounds on the true population proportion p. Of course, you've also got to have a level of confidence to give you that e. But let's talk about what we've got here first. There's the population proportion, that's or p. There's the sample proportion, that's p hat. And of course, we can make the sample proportion out of x and n. It's nothing more than the quotient of x over n. X is the number of successes, and n is the number of samples, the sample size. E is our margin of error. That's the same as before. We get E using z, and z is exactly the z that we used before for a normal distribution. We put that subscript on it to say what the confidence level was that gave us the z. So that confidence level will be our subscript. Remember, the confidence level C is nothing more than the complement of alpha. P hat is exactly what you'd expect, the complement of Q hat, and Q hat is the complement of P hat. The margin of error is Z, that Z score, Z sub C, to remind us the level of confidence that we started the problem with, and we multiply that by the quotient of p hat q hat over n inside of the square root, and that gives us our margin of error. So then we do the statistical interpretation. So we say something along the lines that there's a C% chance, that's our confidence level, that the interval p hat minus e less than p hat plus e, there's our point statistic plus or minus the margin of error, contains the true proportion. Then we say this in words, so that interval contains the true population proportion. The critical value, z sub c, is the bridge between the confidence level c and e, the error, the margin of error. The critical value is a value from the standard normal distribution, that is, it's a z-score. Since a confidence interval, so let's get those out, is found by adding and subtracting a margin of error from the sample proportion, and the interval has a probability of containing the true proportion, then you can think of this as a probability statement. The probability that the true population proportion is in the interval from p hat minus e to p hat plus e is equal to c. Now, we can find this using the inverse normal function on our calculator, or we can find it using Bell. So let's find a few of these. So we're going to use Bell to find the critical values for C equals 95%, 90%, and 99%. So if you've got a calculator, get it out, go into Bell, run Bell, and then that first question says, do you want to calculate a probability, or do you already have the probability and you want to calculate the boundary? Well, we want the z-score, that is the boundary, for these three probabilities. So our first option inside of Bell is going to give us a 1. And then, of course, this is normal, so 0. This is a z-score. And then the next question says, you've got x's or z's. Well, these are z's. The probability for this first question is 0.95. And that's the area inside. We want to capture 95% of that, so the choice for that is 2. And then it tells us that the z-score is 1.95996, which rounds to 1.96. Going through that again for 90%, 0.9, we learned that the z-score for a confidence level of 90% is 1.64, and 99% is 2.58. If you look back at the definition of E, it's z sub c times that square root of p hat times q hat over n. And that is the standard error. It's the closest thing we're going to have to the standard deviation. It's not exactly the standard deviation, but you can think of it along those same lines. One of the interesting things is, even though this is our first look at confidence intervals, the point estimate is always the center of the confidence interval. We find that interval by adding or subtracting the margin of error. And the margin of error is always the critical value times the standard error. Okay, so let's do an example. It says that we're going to use a random sample to estimate a population proportion P, find the 90% confidence interval for a sample of size 500 with 125 successes. So basically just some numbers, and we're going to create a confidence interval. So there's some screenshots of how we're going to find this on our calculator. So let's start going through this. Of course, the first thing that we need to do is declare our variables. So x is the number of successes, so we're going to say that. And this is a proportion question, so P is the proportion of success in the general population, whatever that population is. 2. First thing that we were told is that this is a simple random sample, so that looks good. The next thing we need to do for any proportion is the binomial tests. So just 2 outcomes, either a success or not. This question is not worded in a way that it's difficult to see that. There's a fixed number of trials, in this case n equals 500, and we're assuming that they're independent. Now we also have to check that there are enough of each cases, that there are at least 5 successes and at least 5 failures. So to do that, you might say, well, what is p hat? So we're going to go through this 2 different ways. We're going to use p hat and n and q to ensure that there are enough of each case, but then we're just going to use x and n minus x as well. So first, let's find p hat. P hat is x divided by n. So when we take our number of successes in this example, 125, divided by the sample size of 500, we get 25%. Q is, of course, the complement of that. So q hat is 1 minus p hat. The complement of a quarter is 3/4, so 0.75. So we're going to do this the old-fashioned way. That is, we're going to show that n times p hat is at least 5. So n times p hat is 500 times 0.25. When we do that arithmetic, we get 125, which is at least 5. Now we're going to go through and do that same calculation, ensuring that the number of failures, of not successes, is also at least 5. When we do that, we multiply 500 by 3/4, 0.75, and we get 375, which is greater than or equal to 5. Notice that we didn't have to do all this arithmetic, just like we were looking at before. We could just check that x is at least 5. Remember, x is 125, and that's clearly at least 5. And n minus x, that is everything that's not a success, n being all the trials that we performed, and x being the successes. N minus x is 500 minus 125, which is 375, clearly more than 5, or equal to 5. Now we're going to get out our calculator. So in our calculator, we're going to go, let me get this thing turned on. We're going to go into our calculator. We're going to go into statistics and then over to tests. And then we're going to look for a 1 proportion z interval, 1 prop z int. And on my calculator, you can't see that until you scroll down. So I'm scrolling down until I get to option A, a 1 proportion z interval. So if you're in stats, went over to tests, down to a 1 proportion z interval, you press enter. It asks you for n. I'm going to put in 125, so there's time to follow along if you want to. Or x is 125, n is 500. Our confidence level is 90%, so 0.90, which was already entered, so I'm deleting the fact that I entered it twice, going down to calculate, and then that same screen appears. That's confirming that n is in fact 500 and p hat is 1/4, 0.25. It's also giving us the confidence interval, about 22% to about 28%, 0.21815 to 0.28185. So we're going to go down here, and we're going to state our confidence interval for the true population proportion at a 90% confidence level. Now we need to say this 2 different ways. So we're going to say this as there is a 90% chance, there's C, our level of confidence, that the true population proportion, that's P, is in this interval between 0.21815 and 0.28185. Then we're going to say this in words. Not a lot to say. We weren't told what this question was actually about. We're going to state the interval. So there it is. And we're going to say that it contains the true population proportion. Okay, another example. This one asks us to do exactly what we've done before, but it gives us information in a different way. So when we look at the question, it says, out of a random sample of 159 adults, 68% had kids. Now, that's interesting because that's basically giving us p hat, the proportion of the sample of 159 adults who had kids. So that 68% is p hat. P hat is x divided by n. What we don't have is x. We've got p hat and we've got n. Now notice if you do a little algebra, you can solve for x. It's just n times p hat. So that will give us x. Now based on this, construct a 95% confidence interval for the true proportion in the population of people with kids. So the first thing we're going to do is declare our variables. So we're going to say that the x is the number of adults in our study who have kids, and p is the true population proportion of adults who have kids. Then we need to check our conditions. The first is that this is a random sample, and that's exactly what it says, out of a random sample of 159 adults. The second thing is our binomial tests, independence, the two outcomes, and the fixed number of trials. Then we're going to use our n. So n, remember, is 159, the sample size. And we're going to find x. So we can do this using the formula. Just multiply both sides by n, and we get x equals n times p hat. So when we do that in this example, that's 159 times 68%, which is 108.12. Now, luckily, your calculator won't let you enter an x or an n that's a decimal, and just because it doesn't make any sense. And so we're going to round that to the nearest integer, namely 108. Now we know that x is 108, and 108 is greater than or equal to 5, so that's part of establishing our conditions. The second is n minus x, 159 minus 108, and that's clearly over 5 as well. It's 51. So those are the three things we need to check: that it's a random sample, a binomial, and that there's enough successes and failures, and that's defined to be at least 5 of each. We put this in our calculator, and out pops our interval. So 0.60669 to 0.7518. So we use that then to say that there is a, let's see, what was the confidence level? 95%. There's a 95% chance that that interval contains the true population proportion P. Now we're going to say this in words, and this is what we'd pass off to whoever's paying for it. It says the percentage of adults who have kids is between 61% and 75%, so rounded to the nearest whole percentage.